All right, diving in today, folks. We're taking a look at binary search trees.
Ah, BSTs. Powerful stuff.
Yeah, they're all about organizing data in a really smart way so you can find what you need super fast. We're using lab08trees.pdf as our main guide here.
Great source. It lays out all the core concepts.
So, goal for today's deep dive is to really grasp what makes BSTs so useful, especially when you need to find specific information quickly. No getting lost in the weeds, though. Just the good stuff, the why and the how.
Absolutely. Let's keep it practical.
So before we get into the specifics of binary search trees, let's start with the basics. What exactly are we talking about when we say tree in computer science?
Well, think about a family tree, right? You've got individuals, and they're connected in a specific way to show relationships.
Parents, children, all that.
Exactly. So in computer science, a tree structure is kind of similar. You have these things called nodes, which hold information.
Like each person in the family tree.
Right. And these nodes are connected by edges, which represent the relationships between them.
Okay, so that's a tree in general. But a binary search tree is a special type of tree, right? What makes it different?
Absolutely. BSTs have three key properties that make them unique and super efficient. First, all the nodes in the left subtree of a particular node have values that are smaller than the node itself.
Smaller to the left. Got it.
Second, all the nodes in the right subtree have values that are greater than the node.
Okay, so everything's nicely ordered.
Precisely. And here's the third key point. Both the left and right subtrees have to be BSTs themselves. This is where that recursive idea comes in. It applies all the way down the tree.
So it's like this consistent structure that repeats itself at every level. Makes sense. The lab mentions something called a struct node. What is that exactly?
That's the fundamental building block of our BST. It's basically a structure that holds three things. The actual data you want to store could be a number, a word, whatever, and then two pointers, which are like addresses. One pointer is called left child, and it points to the next node in the left subtree, the one with the smaller value.
And the other pointer.
That's called right child. And as you might guess, it points to the next node in the right subtree, the one with the larger value. So these pointers are what link everything together into that tree structure.
Like the branches connecting everything. So we've got the structure down. Now, what can you actually do with a BST? The lab lists some basic operations. What are those all about?
Right. These are the actions you can perform on a BST. So you've got insert, which is how you add new data to the tree. And remember, when you insert something, it has to follow those ordering rules we talked about.
Smaller values to the left, larger values to the right.
Yep. Then there's search, which is exactly what it sounds like. You're looking for a specific piece of data within the tree. And the cool thing is, because of that ordered structure, searching in a BST is super efficient.
Makes sense. Instead of looking through everything randomly, you know where to go based on the value you're searching for.
Exactly. Now, besides inserting and searching, there are also these things called traversals. These are ways of systematically visiting every single node in the tree.
Kind of like taking a tour of the whole tree and making sure you see everything.
Yeah, that's a good way to put it. The lab mentions breadth first traversal and depth first traversal. Breadth first basically looks at each level of the tree, one after the other, like starting at the top and moving down. Depth first, on the other hand, goes as deep as it can down one particular path before going back up and exploring other paths.
Interesting. And it mentions different types of depth first traversal. What's the deal with those?
Yeah, there's pre-order, in-order, and post-order traversal. The lab doesn't go into too much detail about how those work, but the main idea is just that there are different ways of systematically visiting all the nodes. Think of it like different routes you could take to visit every house in a neighborhood.
Okay, I get the general idea. So the lab also includes some sample syntax for the insert operation. What's the basic logic there? Well, without getting too deep into the actual code.
Sure, so the key to inserting is comparison. You start at the top of the tree, the root node, and you compare the data you're inserting to the data in that node. If the new data is smaller, you go to the left subtree. If it's larger, you go to the right subtree.
And you keep doing that.
Exactly. You keep going down the tree, comparing and choosing left or right until you find an empty spot where you can insert the new data. And the whole time, you're maintaining that order smaller to the left, larger to the right.
So it's like this self-organizing system. Pretty cool. Now, let's bring this all back to the real world. The lab talks about using BSTs for things like indexing actors or movies. Can you give an example of how that would work in practice?
Imagine you're building a movie database. You could use a BST to store all the movie titles.
So each movie title would be a node in the tree.
Exactly. And because of the BST's ordering, the titles would be arranged alphabetically. Now, when a user searches for a specific movie, the system doesn't have to look through every single title in the database. It can quickly navigate the tree, going left or right based on the first letter of the movie title.
So it dramatically speeds up the search.
Right. And to make it even more user-friendly, the lab mentions making the search case insensitive. So users don't have to worry about capitalization. They can just type in the movie title however they want, and the system will still find it.
That's a nice touch. So essentially, a BST is like a super efficient, always sorted list that you can search through really quickly.
Hmm.
Is that the main takeaway, right?
Yeah, exactly. And if you think about it, this idea of efficient searching is crucial in so many areas of computer science and beyond. It's how search engines find information so quickly, how databases retrieve specific records, and even how some algorithms work. BSTs, or other data structures that use similar principles of ordered organization, are often the foundation for these processes.
Really powerful stuff. So to sum it up for our listeners, binary search trees are a clever way to organize data in a hierarchical structure based on value. And this organization is what makes searching incredibly efficient.
And here's a thought to ponder. Where else do you see this principle of hierarchical organization leading to faster access to information in your everyday life? Think about how you organize your own files, or even how information is structured in a well-written book. It's a concept that goes way beyond just computer science.
Lots to think about there. Thanks for joining us for this deep dive into binary search trees.
It's been my pleasure.